Welcome to this coding walkthrough. Today, we'll be solving LeetCode problem number 2089, find target indices after sorting array. In this problem, we'll explore how to sort an array and efficiently locate specific indices. Let's dive in and break it down step by step.
In this problem, you're given a zero-indexed integer array called nums and a target integer. Your task is to first sort the nums array in non-decreasing order, which means arranging the numbers in ascending order. Once the array is sorted, you need to identify all the indices where the target value occurs in the sorted array. These indices should be collected into a list, and this list must also be in increasing order. If the target value is not present in the array at all, the function should simply return an empty list. For the input format, you'll be working with an array of integers, where the length of the array is at least 1 and at most 100. Each element in the array, as well as the target, lies within the range of -100 to 100. The output will always be a list of integers that represent the indices of the target in the sorted version of the array. If the target is not found, the output will be an empty list. Now, let's take a look at some examples to understand this problem better. In the first example, the input array is nums equals 1, 2, 5, 2, 3, and the target is 2. After sorting the array, it becomes 1, 2, 2, 3, 5. The target value 2 appears at indices 1 and 2 in the sorted array, so the output will be 1, 2. In the second example, the input array is the same, nums equals 1, 2, 5, 2, 3, but the target is now 5. After sorting, the array is again 1, 2, 2, 3, 5. Here, the target value 5 appears only at index 4. So, the output is 4. Finally, in the third example, the input is still nums equals 1, 2, 5, 2, 3, but the target is 4. After sorting, the array is 1, 2, 2, 3, 5, and we see that the target value 4 does not appear in the array. Therefore, the output is an empty list. Now, let's discuss the constraints and edge cases for this problem. First, the length of the array nums is guaranteed to be between 1 and 100. Each element in the array lies between -100 and 100, and the target value also falls within this range. There are some important edge cases to consider. For example, if the target value is not present in the array, the output should be an empty list. This happens in cases like nums equals 1, 2, 3, and target equals 4. Another scenario is when all elements in the array are the same and equal to the target, such as nums equals 2, 2, 2, and target equals 2. In this case, the output should include all the indices of the array. Finally, for a single element array, such as nums equals 5 and target equals 5, the function should still handle it correctly and return 0 if the target matches the element, or an empty list if it does not. To solve problem 2089, we start by understanding the general requirements, sorting the array nums in non-decreasing order and identifying all indices where the target value appears. One straightforward way to approach this is the brute force method. First, we sort the array in ascending order. Then, we iterate through the sorted array and collect the indices where the value matches the target. This approach, while simple and intuitive, has a time complexity of (n*log n) due to the sorting step, with an additional (n) cost for iterating through the array to find the target indices. While this method is effective for smaller inputs, it can be inefficient for larger arrays because it involves sorting even when we only need the target indices. This makes us question whether we can optimize the process further. An optimized approach involves using binary search to improve efficiency. After sorting the array in ascending order, we use binary search to locate the first occurrence of the target value. Then, we perform another binary search to find the last occurrence of the target. Once we have these two positions, we can easily gather all the indices between them. The key advantage of this method lies in its efficiency. Sorting still takes (n*log n), but binary search reduces the time spent finding the target to (log n) for each search, leading to an overall time complexity of (n*log n). This approach is particularly useful for larger arrays where the target appears multiple times, as we avoid iterating through the entire array unnecessarily. However, it's worth noting that this method is slightly more complex to implement compared to the brute force approach.
Another alternative approach involves counting occurrences without fully sorting the array.
Here, we first count how many elements in nums are less than the target to determine the starting index after sorting. Then, we count how many elements are equal to the target, which gives us the range of indices where the target would appear. Using this information, we can construct the result without explicitly sorting the array. This method is highly efficient, achieving an overall time complexity of O(n), as counting elements is linear and constructing the result depends only on the number of target occurrences. However, this approach comes with trade-offs. It may require additional space for maintaining counts, and the implementation is more complex due to the counting logic.
While it avoids sorting, the gain in efficiency may not justify the added complexity in many scenarios.
The strategy we choose for this problem is the optimized approach that combines sorting with binary search. While the brute force method is simple, it becomes inefficient for larger inputs due to the need to iterate through the entire array after sorting. On the other hand, the counting approach improves efficiency but introduces unnecessary complexity, especially when sorting the array provides a straightforward solution. The optimized approach strikes the right balance between simplicity and performance. Sorting the array helps simplify the problem, and binary search allows us to efficiently locate the range of indices where the target appears. This method is both scalable and relatively easy to implement, making it the most practical and balanced choice for this problem. By leveraging this strategy, we ensure the solution is robust and efficient, while minimizing unnecessary complexity. The goal of this problem is to determine the indices of all occurrences of a specific target value within a sorted version of an input array. To achieve this, we first sort the unsorted array in non-decreasing order. This sorting step is crucial because it ensures that all the indices of the target value will be grouped together, making it easier to locate them. For instance, if our input array is 4, 2, 3, 4, and the target is 4, sorting the array transforms it into 2, 3, 4, 4, where the target values are now consecutive. Once sorted, we identify the starting index of the target by traversing the array until we encounter the first instance of the target value. In this example, the first occurrence of 4 is at index 2. This marks the beginning of the target's range, simplifying our next step, which is to collect all indices where the target appears. After finding the starting index, we continue scanning through the sorted array to collect all indices where the target value occurs. As we traverse, we add each matching index to a result list. This process stops as soon as we encounter a value that is no longer equal to the target, ensuring that only consecutive indices corresponding to the target are included. For example, in the sorted array 2, 3, 4, 4, with a target of 4, we begin at index 2 and collect both indices 2 and 3 since those are the positions where the target appears. Once complete, we return the result list, which in this case is 2, 3. A few key insights emerge from this approach. First, sorting is a foundational step because it guarantees that all target values are grouped together. Secondly, the algorithm is efficient, with an overall time complexity of O(n) log n, due to sorting and an additional O(n) for traversing the array. Lastly, we must handle edge cases, such as when the array is empty, the target is absent, or all elements in the array are equal to the target. To implement this algorithm, we start by sorting the input array in non-decreasing order. This modifies the array in place and ensures that target values are grouped together. Next, we initialize an empty list to store the indices of the target. Using a loop to traverse the sorted array, we check each element to see if it matches the target. When a match is found, we append the current index to the result list. This process continues until all target values are accounted for. Finally, we return the result list containing the indices. Here's the Python implementation. After sorting the input array using nums.sort, we initialize an empty list called result. We then iterate through the array, and for each index where the value equals the target, we append the index to result. The function concludes by returning the result list, which contains all indices of the target in the sorted array. Analyzing the complexity of this solution, the time complexity is dominated by the sorting step, which takes O(n) log n. Traversing the sorted array to find and collect the indices of the target takes an additional O(n). Therefore, the overall time complexity is O(n) log n. For space complexity, the sorting operation is performed in place, meaning no additional space is used for the sorting process.
However, we do require OK space to store the result list, where K is the number of indices matching the target value.
Thus, the overall space complexity is OK.
This balance of time and space efficiency makes the algorithm well-suited for solving the problem within the constraints provided. This Python implementation solves LeetCode problem number 2089, find target indices after sorting array using an efficient and straightforward approach.
Step-by-step explanation.
1. Sorting the input array. The first step is to sort the array nums in non-decreasing order. This ensures that all elements are arranged in ascending order, as required by the problem. Python nums.sort.
Sorting is handled using Python's built-in sort method, which operates in n log n time complexity. Sorting is necessary because the problem requires indices of the target value in the sorted array.
2. Initializing an empty result list.
We create an empty list called result to store the indices of all occurrences of the target value.
Python result equals 3. Iterating over the sorted array.
Using a for loop, we traverse the sorted array.
For each element, we check if it matches the target value. If it does, we append the current index to the result list. Python for I in range, len, nums. If nums, I, equals target. Result.append, I.
This loop runs in n time complexity, where n is the number of elements in the array. The conditional check ensures that only indices of elements equal to target are added to result.
4. Returning the result. After the loop completes, the result list contains all indices where the target appears in the sorted array. The list is returned as the final output. Python return result.
Example walkthrough.
Suppose the input array is nums equals 1, 2, 5, 2, 3, and the target equals 2. Sorting, after sorting, nums becomes 1, 2, 2, 3, 5. Iteration, the loop processes each element. Index 0, value is 1, not equal to 2. Index 1, value is 2, equal to 2, append index 1 to result. Index 2, value is 2, equal to 2, append index 2 to result. Indices 3 and 4, values are 3 and 5, not equal to 2. Result, the final result equals 1, 2, is returned.
Complexity analysis. Time complexity, the sorting step takes n log n, and the iteration step takes n. Overall, the complexity is n log n. Space complexity, the solution uses 1 extra space apart from the input and output.
This approach is efficient and adheres to the problem constraints.
Here, we start by importing the necessary utility classes from Java, such as java.util*, to leverage data structures like arrays and lists. The solution is encapsulated in a class called solution, following Java's object-oriented design principles.
In the target indices method, we first sort the given array nums in non-decreasing order using arrays.sort.
Sorting ensures that the indices of the target elements align with their positions in ascending order. Next, we initialize an empty list named result to store indices where the target value is found.
We then iterate through the sorted array using a for loop. During each iteration, we check if the current element matches the target value. If it does, we add the current index to the result list. This ensures that all matching indices are captured.
Finally, the method returns the list of target indices, which is the desired output of the function.
To demonstrate how this function works, we include an example in the main method. Here, we create an instance of the solution class and define an input array nums with values 1, 2, 5, 2, 3, along with a target value of 2. When we call the target indices method and pass these parameters, it sorts the array, finds the indices of the target value, and returns them in a list. The indices are then printed to the console, and the output in this case is 1, 2. This output corresponds to the positions of the target value after sorting the array.
This simple yet effective implementation highlights how sorting and iteration allow us to find the desired indices efficiently.
To solve this problem, we start with an example where the input array is 1, 2, 5, 2, 3, and the target value is 2. The first step is to sort the array. Before sorting, the array is 1, 2, 5, 2, 3. Once sorted, it becomes 1, 2, 2, 3, 5.
Sorting ensures that all occurrences of the target value appear consecutively, making it easier to identify their indices. Next, we initialize an empty list called result where we will store the indices of the target value as we find them during the iteration process.
Now, we iterate through the sorted array and check each element against the target value. In the first iteration, the value at index 0 is 1, which does not match the target value of 2, so no changes are made to result. In the second iteration, at index 1, the value is 2, which matches the target, so we add index 1 to result. In the third iteration, the value at index 2 is also 2, so we add index 2 to result as well. At index 3, the value is 3, which does not match the target, so result remains unchanged. Finally, at index 4, the value is 5, which again does not match the target, so no further changes are made. After completing the iteration, result contains 1, 2, which are the indices of the target value in the sorted array. We then return this result as the output. In another example, the input array is 4, 5, 6, 7, and the target value is 3. The first step is to sort the array. Since the array is already sorted, it remains 4, 5, 6, 7. With the sorted array ready, we initialize an empty list called result to store any indices of the target value that we find. Next, we begin iterating through the array to check each element. At index 0, the value is 4, which is not equal to the target value of 3, so no changes are made to result. At index 1, the value is 5, which also does not match the target, so again, no changes are made. Similarly, at indices 2 and 3, the values are 6 and 7, respectively, neither of which matches the target. As a result remains empty throughout the iteration. Since no indices were found, we return an empty list as the output. In a third example, the input array is 1, 1, 1, 1, and the target value is 1. The first step is to sort the array. Since all elements are already the same, the array remains 1, 1, 1, 1 after sorting. With the sorted array in place, we initialize an empty list called result to store the indices of the target value. Then, we proceed to iterate through the array to identify the indices where the value matches the target. During the iteration, at index 0, the value is 1, which matches the target, so we add index 0 to result. At index 1, the value is again 1, so we add index 1 to result. Similarly, at index 2, the value matches the target, so we add index 2 to result. Finally, at index 3, the value is 1, so we add index 3 to result. After completing the iteration, result contains 0, 1, 2, 3, which are all the indices of the target value in the sorted array. We then return this list as the output. To analyze the time complexity of our solution, we need to break it down into its two main components, sorting the array and iterating through it to find the target indices. First, we have the sorting step. Here, we use Python's built-in sort method, which relies on the timsort algorithm. This algorithm offers a time complexity of O, n log n, for an array of size n. Next, the iteration step comes into play. Once the array is sorted, we traverse through it to identify the indices where the elements match the target. This traversal involves a single pass through the array, which takes O, n, time. Additionally, for every matching element, we append its index to the result list. Since the append operation is O, 1, and can occur up to n times in the worst case, the appending step is dominated by the iteration and sorting steps. Altogether, these operations define the core time complexity of our solution. Now, combining these steps, the total time complexity becomes the sum of sorting and iteration, O, n log n, for sorting, plus O, n, for traversing the array. Since O, n log n, dominates O, n, the overall time complexity is O, n log n. Shifting our focus to space complexity, we consider both the input and output requirements. The input array, nums, is sorted in place using timsort, meaning no additional space is allocated for sorting the array itself. For the output, we use the result list to store the indices of elements matching the target. In the worst case, where all n elements match the target,
the result list would grow to size n, requiring O(n) space. Finally, the auxiliary space used by TimSort itself is O(n) in the worst case, as it needs temporary storage while sorting. These factors combine to define the space complexity of our solution. Overall, the space complexity is determined by the auxiliary space required during sorting and the space needed for the result list. Both of these are O(n), so the total space complexity is O(n). Let's now examine the best, average, and worst case scenarios. In the best case, the array might already be sorted, or it might contain no elements equal to the target. However, the sorting step will still take O(n log n) time, as TimSort doesn't avoid sorting entirely even for already sorted inputs. The space complexity remains O(n) due to the auxiliary space and result list. In the average case, the sorting step again dominates, resulting in O(n log n) time and O(n) space. In the worst case, where all elements are equal to the target, the time complexity is still O(n log n) due to sorting, and the space complexity remains O(n). Thus, there is no variation in complexity between these cases. To put these insights into context, let's compare the given solution to a naive or brute force approach. A brute force method might involve iterating through all n elements to collect the indices of the target values. While this direct iteration would be O(n), it does not ensure that the indices are returned in sorted order. Sorting the collected indices afterward would require O(k log k) time, where k is the number of target elements. Since k can be as large as n, the overall time complexity of the brute force approach becomes O(n log n) in the worst case, similar to our optimized solution. However, the optimized approach has a significant advantage. By sorting the entire array first, we guarantee that the indices are already in sorted order without needing additional processing. This makes the given solution not only clear but also efficient for handling larger arrays. In summary, the key takeaways for the time and space complexity of this solution are as follows. The time complexity is O(n log n), driven primarily by the sorting step, while the space complexity is O(n), accounting for the auxiliary space during sorting and the result list storage. The best, average, and worst case scenarios all share the same complexities, O(n log n) for time and O(n) for space. Compared to a brute force approach, the given solution is more efficient and guarantees correctness by leveraging sorting to ensure the indices are returned in order. This makes it an optimal and robust approach for solving the problem. When solving this problem, there are several common mistakes to watch out for. First, attempting to find the target indices before sorting the array is a frequent error. This approach fails because the indices of elements in the sorted array differ from their positions in the unsorted array, leading to incorrect results. Another issue arises with edge cases, such as when the target value is not present in the array. Neglecting to handle these scenarios can cause runtime errors or lead to outputs like uninitialized values. Additionally, using an inefficient sorting method, such as bubble sort, can unnecessarily increase the time complexity, which is especially problematic for larger input sizes, like arrays with tens of thousands of elements. Finally, while some solutions use a linear search after sorting to find target indices, this is suboptimal. A better approach is to leverage binary search, which can reduce the complexity of locating the range of target values in the sorted array. Another mistake to avoid is directly modifying the input array by sorting it, especially if the problem specifies that the input must remain unchanged. Sorting in place can lead to unexpected side effects elsewhere in the code. From an interview perspective, it's important to highlight the use of efficient sorting algorithms such as quicksort or mergesort, which are often implemented in built-in methods like Python sort or Java's arrays.sort. These methods operate in O(n log n) time, making them optimal for this kind of problem. Binary search is another crucial technique to emphasize. It allows you to efficiently locate the range of target values in the sorted array, reducing search complexity to O log n. Be prepared to handle edge cases as well, such as empty arrays, arrays with all identical values, or when the target is absent. Lastly, consider the space complexity of your solution, such as whether additional memory is used for copying the array, and explore ways to minimize it where possible. To deepen your understanding of this problem, you can practice related problems that involve similar concepts. For example, LeetCode 704 introduces the basics of binary search, which is essential for efficient solutions. LeetCode 35, Search Insert Position,
also involves binary search to determine the correct position for a target in a sorted array. LeetCode 852, peak index in a mountain array, provides practice with binary search in a scenario involving a sorted-like structure. Lastly, LeetCode 1838, frequency of the most frequent element, combines sorting techniques with target-based analysis, offering a more advanced challenge. These problems reinforce the key skills needed to solve variations of the current task effectively. There are several alternative approaches to solving this problem, each with its own trade-offs. The brute force method involves iterating through the array to find all the indices of the target after sorting. While this approach is simple and intuitive, its time complexity is O, n log n, for sorting and O, n, for traversal, making it less efficient for larger inputs. A more efficient option is the binary search approach, which uses binary search to locate the start and end indices of the target range after sorting. This method has the same O, n log n, sorting complexity but reduces the search time to O, log n. However, it requires a solid understanding of binary search implementation. Another highly efficient approach is targeted counting sort, where you count the occurrences of each number in the array and directly calculate the indices for the target. This method achieves O, n, complexity for both counting and index computation, but it's only practical for problems with small, bounded values. Each approach has its strengths and weaknesses, so the right choice depends on the specific problem constraints and requirements. Great job making it to the end. To summarize, we address sorting and index identification efficiently, key concepts to practice for coding interviews. Remember to explore similar problems to strengthen your skills. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!